Hi, everyone. I want to thank everyone for coming, first of all, and also thank my advisor, Dr. Tom Pingle, and committee, Drs. Tina Dora and Yang Shao, for all their help and guidance along this project. So, my thesis is titled Comparing UAV and Pole Photogrammetry for Monitoring Beach Erosion. So to introduce the problem of beach erosion, in a beach environment, the sand is constantly shifting to the loose nature of the sand and constant wind, wave, and tidal forces. In the United States, the majority of beaches were already experiencing a general erosion trend by the year 2000, and this is only expected to accelerate as sea levels rise, causing more situations like what you can see in this photo here, with homes, roads, and other buildings being washed into the ocean. In addition, a healthy beach and dune system is a really effective barrier against storm surge and flooding. And so erosion can also put buildings that are further away from the beach at greater risk, not just the buildings and homes that are directly on the beachfront. And because erosion can totally sweep away buildings like you see here, which is a pretty extreme case, or just increase vulnerability to the surrounding area, monitoring erosion is an essential part of an effective management program to know what steps must be taken to mitigate land loss and storm vulnerability. And on the US East Coast, most of this erosion is caused by a mix of wave and tidal forces. We have these really sandy, long chain of barrier islands running up and down the East Coast. This often occurs in seasonal cycles where larger waves are generated by the higher wind speeds and storms in the winter months, causing erosion, removing sand from the beach. And then during the calmer summer months, some of the sand that was eroded in the winter can actually be pushed back up onto the beach, causing accretion, where the beach actually grows a bit. In addition to these seasonal cycles, major storms can wash away massive amounts of sand in just a few hours. In the animation you can see here, Hurricane Hugo hit in 1989, which caused 28 meters of shoreline retreat essentially overnight. And you can also see how active the beach is near the inlets, where these sandbars gradually move sand from one island to the next. The longshore drift here is generally from north to south. The sandbars that form the ebb tidal deltas will gradually weld to the southern side of the inlet, and that sand will get distributed along the island until it eventually moves on to the next island to the south, kind of jumping across the inlet there. To give some background on erosion monitoring practices, various strategies have been employed to monitor and measure erosion, including the traditional ground-based methods that now use RTK GPS systems, previously stadia rods, survey chains, etc. Then aerial photography, especially from the Second World War and onwards, like you can see on the left here, which shows the recovery of a beach in the years following Hurricane Hugo. The top image was taken immediately after the storm, where you can see this inlet is very washed out due to the high storm surge, large waves, and everything. And the bottom image was taken a few years after the storm, after things largely recovered to a more normal state. And with the advent of remote sensing technologies, Lidar has become a very mature method for topographic surveying, and then within the past decade, photogrammetry has become quite popular as well. Since drones became much more common and accessible in the mid-2010s, UAVs and photogrammetry have been extensively used for topographic surveying, including in a beach environment. And in addition, pole photogrammetry has been shown to be a viable alternative for measuring elevation and geomorphic change in situations where UAV flight might be impossible. Mancini et al. In 2013 was the first study to employ and evaluate UAV photogrammetry for beach surveying. And they found that photogrammetric point clouds have very good accuracy, and the system is both faster and easier to use than a terrestrial laser scanner. Turner et al. In 2016 demonstrated the operational utility of UAVs, where they implemented drone surveys on a beach in Australia that has been used as a test bed for erosion monitoring practices for the past 40 years, and completed 2 years of post-storm surveying and monthly surveys, and directly compared and verified the UAV surveys against their existing operational surveying practices. Scarelli et al. In 2017 showed that UAVs are effective in identifying seasonal, natural, and anthropogenic changes in a beach and dune system using the DEM of difference method, which we'll be using later here. And both Scarelli and Turner note that the high quality of drones ready for photogrammetry work are now available off the shelf for relatively low cost compared to the more expensive LiDAR units or very labor-intensive ground-based surveying methods. However, these studies do note a few key limitations of UAVs, mainly the inability to operate in poor weather, and then the training required to understand and then abide by flight regulations, which might restrict flight in certain areas. Rossi in 2017 notes that photogrammetry is useful for monitoring geomorphic change and explores pole photogrammetry as an alternative to drones in a situation where flight is impossible. Rossi finds that pole photogrammetry is effective in monitoring sandbars in these steep, sinuous canyons in the American West, where drone flight is not very practical due to the tight canyon walls, and that pole photogrammetry works best in areas of 10 to 1,000 square meters or 1 hectare in size, and areas that have little or no vegetation cover. So the objective of this study is to compare and evaluate UAV and pole photogrammetry for routine monitoring of beach erosion, comparing both systems based on their performance and feasibility. Our hypothesis is that UAV photogrammetry is going to be better suited for beach erosion monitoring, but that pole photogrammetry will present a viable alternative when UAV flight is not an option. The photogrammetry workflow used here is known as structure from motion, which uses a series of overlapping images to find matching points in these images and then build a 3D reconstruction of an object. As the name implies, these images are usually obtained from a platform in motion, like a flying drone. Unlike earlier photogrammetry systems, structure from motion does not require any prior knowledge of the camera pose and position, and it can determine these from the images themselves, although providing this information prior to processing, if you have it, does accelerate processing and improve the results. Structure from motion can use any digital camera, provided that important camera and lens distortion characteristics are known. It's very fast and easy to use with good accuracy and very high resolution, and the ease of conducting surveys makes structure from motion great for these regular repeated surveys. However, there are some common errors that are associated with structure from motion. One is known as ghosting, where a single surface is recreated as multiple vertically offset layers, appearing as a sort of double image. It's difficult to determine which layer represents the true surface, and thus it is impossible to accurately determine the elevation of the surface. When generating a digital elevation model or surface model from a point cloud with ghosting errors, it results in these sharp ledges and platforms that you can see in the digital surface model in the top right, which should be one smooth continuous gradient if there are no errors present, but instead we have these clear breaks and ledges. And in the animation below, we can see the point cloud used to generate the above digital surface model. It initially appears as one fairly smooth surface, but as we zoom into the side, we can see that it's broken into these multiple vertically offset layers. This ghosting is caused by poor image calibration, preventing the structure from motion software from finding accurate key points. And without a sufficient number of matching accurate key points, it will place the same real-world feature into multiple locations in this digital space. Another issue is doming, where a surface appears unnaturally curved, with a negative bias in the center that gradually shifts to a positive vertical bias towards the edges, or vice versa. In the animation here, you can see as we move to the side view that the point cloud has a slight concave curvature, which results in a negative vertical bias, shown by the blue region in the above DSM, gradually shifting to a red positive bias, whereas it should show an even gradient roughly from top to bottom, where the beach is highest at the dune ridge and then lowest at the water's edge. This doming is caused by using an inaccurate camera model that fails to accurately correct the lens distortion or other parameters. And although there are several ways to alleviate doming, it's best fixed by finding an accurate camera model. UAVs are a well-documented platform for topographic structure from motion surveys, as they're easy to use, relatively inexpensive, and there are many off-the-shelf systems on the market that are ready for immediate use. However, they are limited by poor weather and government regulations, especially the prohibition on flying over crowded areas, such as a popular beach. As an alternative, pole photogrammetry can use a camera atop a tall pole to provide a similar aerial perspective, but can operate in situations where drones cannot. The downsides of pole photogrammetry are that it is much slower, and the lower altitude and smaller field of view means that more images are required, leading to much longer processing times. The study area used here is a 200 by 100 meter, 2 hectare stretch of beach near the southern end of beautiful Capers Island, South Carolina. The study area is located near the tidal delta, where it is heavily affected by the shifts in tidal channels and offshore sandbars. Like you can see right next to the study area is this tidal channel where mainly the outgoing tide will flow through, and then across the channel is the sandbar, which is constantly shifting and moving around as the tides and waves push sand around. To the north is the Cape Romaine National Wildlife Refuge, and Capers Island is the southern end of one of the longest stretches of undeveloped coastline on the US East Coast before the Charleston metropolitan area begins to the south. Sediment transport here is generally north to south, meaning that the popular Charleston area beaches, especially Dewey's, Isle of Palms, and Sullivan's Islands, all depend on Capers Island and the other islands to the north for their sediment flow. Capers Island hasn't experienced any major erosion events since Hugo in 1989, but it has experienced some smaller storms in that time and a gradual persistent erosion trend for at least the past 20 years. The drone used in this study is a DJI Mavic Pro 2, which is a small quadcopter drone with a gimbaled 20 megapixel Hasselblad camera with a 28mm equivalent field of view. And it can fly for about 15 to 20 minutes on a fully charged battery, which is enough to cover the study area in a single flight. The pole photogrammetry system consists of a GoPro Hero 8 camera carried atop a 12-foot pole, with the camera angled about 10 degrees above nadir, or in other words, 10 degrees above looking straight down. We also use two MLID RTK GNSS units, which RTK is a highly accurate type of GPS receiver with about 2 to 3 centimeters of accuracy. These were used for the ground control point survey using the RS Plus for the rover unit and the RS2 for the base station. And then we corrected these using a nearby core station or continually operating reference station. And all the photogrammetric processing was done in the Pix4D photogrammetry software suite. We conducted 3 monthly surveys using all 3 of these platforms in September, October, and November of 2020, all at low tide to maximize the surveyable area. Multiple drone flights were flown each month at 50 and 115 meter altitudes with a mix of nadir and off-nadir imagery and single and double grid flight paths. The pole survey consisted of a single grid path consisting of about 20 parallel transects with roughly 4.5 meter transect spacing, and the camera set to take a photo every half second, which gave us about 70% side overlap between images in each transect and over 90% vertical overlap between images, which should be plenty for the structure for motion software. We also used some Lidar data, which Lidar stands for light distance and ranging, and it determines the distance between the sensor and target by shining a laser at the target and then measuring the amount of time it takes for their reflection to bounce back and reach the sensor. Lidar is commonly used to generate high-resolution digital elevation models, or DEMs, and the sensor is typically mounted on an airplane, which enables it to survey very large areas rapidly. Presently, Lidar is the most commonly used method for rapid topographic surveying, and public Lidar data resources provide historical context to our 3 months of photogrammetry surveys. The three DEMs were downloaded from 2018, 17, and 16 from NOAA's Digital Coast portal, and these were used to determine elevation changes between these Lidar flights and our structure for motion surveys. And then earlier data sets from 2010, 2006, and 1997 were not available as DEMs, but they were available as digital surface models or point clouds. And due to the drastic erosion over this long time period, the present-day beach was actually covered by forest in these older data sets, so they weren't very useful for elevation comparison, but they are useful to map the shoreline retreat. We can clearly see where the Fordune Ridge lies in these surface models and use that as a landmark to kind of mark how the shoreline has changed over the years. For the Pix4D processing of the drone imagery, all flights from each survey were processed together to provide multiple altitudes and camera angles, with the vertical accuracy of each image's location set to 1 meter to mitigate any doming errors, and then later geo-referenced using the marks left in the sand by the RTK survey as ground control points. We produced 5 centimeter, that is 1 pixel every 5 centimeter DSMs and orthophotos for later analysis. The processing of the pole photogrammetry initially followed a similar straightforward workflow, but it led to some very severe errors, often resulting in many images not calibrating at all. You can see this in the left-hand image where each red dot represents an image that failed to calibrate and thus failed to reconstruct anything. When images did successfully calibrate, they produced these very severely domed reconstructions, often broken into multiple separate pieces like you can see on the right. Thinking that these image sets of 6,000 to 8,000 images for each pole photogrammetry survey were simply too much for Pix4D to handle, we began processing using only every 3rd image, which didn't decrease the quality, but it did significantly reduce the processing time, whereas previously with the full image set, the first step of Pix4D can take over 24 hours. We found that the GoPro's onboard GPS had very poor accuracy, especially in the vertical axis. The error was actually greater than the roughly 3 meter or so elevation difference between the highest and lowest point of the beach, whereas the GPS error was more like 4 to 5 meters. So then we tried applying a uniform elevation value instead of using the GPS elevation, and then later geo-referenced the reconstruction with ground control points. And we found that the ground control points can also help to reduce errors. However, there are still plenty of breaks, ghosting, and doming errors. We experimented with every setting available in Pix4D, which sometimes led to some really bizarre results, like the curls you can see in this image. We also tried to break the image down, or break the project down into smaller sub-projects, but this didn't really improve anything. And it even introduced some more breaks and seams where we stitched these smaller projects back together. So Pix4D relies on the digital camera model, which contains all the relevant camera spec information, such as the focal length, distortion parameters, and sensor size. And the accuracy of the camera model has been shown to have a large impact on reconstruction quality. Finally, after a few months of troubleshooting, we found a major issue with the camera model we were using. Pix4D has a database of models for common cameras, which are usually very accurate. However, the GoPro Hero 8 model is severely off. It incorrectly lists it as a perspective lens, while it should be a fisheye lens, which vastly changes the distortion parameters and the way that the software corrects for the distortion. Using a modified camera model based on earlier GoPro cameras greatly improved the results, but did not totally fix everything. So the final pole photogrammetry workflow we settled on was to first run step 1 of Pix4D with every third image using altitude estimated from the RTK survey. We then applied manual tie points to fix ghosting and any seams until the positive returns diminish. Although manual tie points can really help to fix any errors, they can also start to negatively impact the reconstruction after adding, say, 40 to 100 manual tie points. Finally, the project was geo-referenced, and then we produced 5 centimeter DSMs and orthophotos like we did with the drone surveys. To compare the UAV and pole photogrammetry, we noted the presence of any errors or artifacts in the reconstructions, notably ghosting and doming. We also compared the minimum or maximum resolution, cost, including the equipment, any necessary training, and the time and cost of conducting and processing surveys. To evaluate feasibility, we determine how useful the platform is in an operational beach surveying scenario, and if the cost or time required make it useful or make it prohibitively expensive to actually use in the real world. To track changes in the beach, we used the DEM of difference method, where we take an earlier DEM and subtract that from a later DEM to show the elevation difference between these two data sets and how the elevations changed over time. This technique is widely used to track geomorphic change, such as by Scarelli et al. And Lamoff et al., which both apply the DEM of difference method in a coastal environment. DEMs of difference were calculated between the monthly surveys as well as between our final November survey and the previous Lidar surveys we downloaded. Although we were using digital surface models generated by Pix4D, because the bare sand is the only surface here with no vegetation or other land cover, just the bare ground, the DSMs and DEMs are essentially interchangeable. To track shoreline retreat, we mapped the location of the foredune ridge and structure for motion in Lidar DSMs from 1997, 2006, and 2010 to provide a consistent landmark rather than the shoreline, which constantly varies with the tidal stage. The drone products were very high quality, with no instances of ghosting. Doming was present in the September DSMs, but not in the October and November, making these two excellent for elevation comparison. All the orthophotos turned out well and are very useful to measure overall beach shape and width. The maximum resolution depends on flight altitude, with all our surveys producing a maximum resolution of about 1¼ centimeter per pixel. Unfortunately, the pole photogrammetry products did not turn out as well. While they produce extremely high resolution as fine as 3 millimeters per pixel, they are riddled with these ghosting artifacts and seams between transects, making elevation comparisons impossible. The September survey also showed doming similar to the drone survey from the same month. And in the orthophoto, the GoPro's automatic shifts in white balance caused inconsistent color temperature, which only accentuates any of these seams you can see in the bottom right here, where you can pretty easily tell where each transect was. The pole photogrammetry performed best near the dunes where there's more vertical relief, and there are more large features like these pieces of driftwood or mats of reeds that are washed up by the tide. The worst performance came away from large relief and features on these flat, uniform sections of the beach with few seashells or anything. In particular, the tight, ribbled surface you can see in the bottom right was especially difficult to reconstruct, and it was also very disorienting to look at closely when trying to locate features like seashells or anything else that we could mark as manual tie points. While the addition of manual tie points can help to alleviate ghosting, it's really easy to incorrectly mark the manual tie points in these areas, which only worsens the reconstruction. Due to doming in the September survey, DEM's difference using the September DSM only really showed the doming artifacts rather than the true elevation changes. You can see this in the bottom right, but there's this shift across the image from blue to red that is entirely caused by the doming, not actual elevation changes. However, the October-November DEM of difference does an excellent job of showing erosion and accretion. On average, the beach eroded by 24 centimeters vertically over this time period for a total volume change of about negative 7,000 cubic meters. The dunes showed essentially no change, while the beach eroded in some places and accreted in others. Most of the severe erosion was in the central area near the water's edge, where the channel appears to have meandered shoreward, eroding the beach by over 1 meter. The foot of the dunes also eroded slightly, as can be seen by the sharp white to blue gradient just before the dunes. Just to the right of this, the channel meandered away, causing the beach to widen a bit and also grow less steep. And the elevation here, therefore, increased. The left-hand portion of the beach, where there was the least elevation change, although we can see these faint alternating bands of erosion and accretion, although the difference is much smaller than what we see further towards the right in the central portion of the image. The drone orthophotos turned out very well. Even in September with the doming and the DSM, the orthophotos showed no errors. They had a maximum resolution of nearly 1 centimeter, and they all show a very high amount of detail. They were most useful for showing changes in the beach shape and width. And even on a short time scale, significant changes are evident, especially towards the right, where the meandering of the tidal channel causes the beach to grow wider in some places and then narrower in others. In October, we can see this bulge that grows in the center area, but then it's completely eroded just 4 weeks later as the beach retreats. And there's actually a slight indentation where there used to be a bulge outwards. The Lidar DEM's difference utilized the November drone survey and Lidar flights from 2016, 17, and 18 that consistently showed elevation in the erosion in the central portion, indicating that the tidal channel does not usually meander this far shoreward. However, they also show that towards the left-hand side of the image, the beach is accreted significantly. The wavy pattern and high accretion indicate that the tidal channel used to be farther shoreward, but has now moved farther out to sea, and the beach therefore has grown much wider in the southwestern portion of the study area. Due to drastic erosion and shoreline retreat, the older Lidar DSMs aren't useful to quantify elevation change compared to the modern DSMs, as the present-day beach face was previously covered by forest. However, by mapping the foredune ridge, we can see how the shoreline retreated over this time period. We use the dune ridge because the actual shoreline is highly variable with the tide, migrating by up to 150 meters every 6 hours. So the dunes act as a more stable and identifiable landmark. We don't know exactly what time of day or what tidal stage these Lidar surveys were taken at. So this is just something that isn't going to be so variable and so noisy as the actual shoreline would be. Towards the right, we see a very pretty steady trend of a shoreline retreat of just a few meters per year. Then the largest change is towards the left-hand side where the front beach turns this corner to the inlet. Here, the dune ridge retreated by nearly 100 meters and took on a much softer corner shape. The presence of an overwash fan where storm surge washed over the dune ridge and pushed sand back into the marsh, circled in red here, indicates that this is due to at least one significant storm event which pushed the dunes further back. Moving on to the cost and feasibility assessment, the drone system is initially more expensive, but is about $3,000 for the drone, several spare batteries and controller, and all the other necessary pieces. while the pole photogrammetry system is only about $500 for all the components, bulk of that being the camera. And this does not require any formal training, while the UAV requires the FAA Part 107 certification, which does take some time and money to prepare for and then take the test. For time, the drone is much faster and can cover the 2-hectare study area in as little as 15 minutes versus an hour and a half for the pole photogrammetry survey. The drone surveys can be planned ahead of time and are then flown autonomously, only requiring the operator to maintain eye contact and take action in case anything goes wrong. This also makes the flights very easily repeatable for routine monitoring. You can essentially just copy and paste the same flight plan and then execute it again. Meanwhile, the pole photogrammetry system is entirely manual and requires constant attention as you're walking around carrying this pole with a camera on it. And the only major drawback of UAVs are the weather and regulation limitations, which don't affect the pole photogrammetry system. The UAV requires wind speeds of less than 10 meters per second or so, with good visibility and no precipitation. The only weather limitations affecting the pole system are lightning and high wind speeds, which make the pole very unwieldy, and also lightning, of course, is very dangerous, holding the pole in the air. Because the drone flies at a much higher altitude, more area is covered in each image, and then fewer images are needed in total. A high altitude drone flight may cover the entire study area and fewer than 100 images, while the pole photogrammetry system takes about 6,000 to 8,000 images, significantly increasing the processing times, even when using only a third of the total image set. In addition, the presence of so many ghosting errors takes an extremely long time to fix, with each manual type point taking roughly 5 minutes or so to properly mark, and then each survey included 40 to 100 manual type points. Moving on to the quality of the products, both systems produced very high resolution DSMs and orthophotos, well above the necessary level for this type of erosion monitoring. For comparison, modern Lidar DMs are often available at 1 meter resolution and are plenty sufficient for this task. The maximum resolution is unnecessary for this project, and it can produce some very large and cumbersome files to work with, especially the pole photogrammetry. The drone products are of much higher quality than the pole photogrammetry products and are largely free from the systematic ghosting errors that make the pole dataset so unusable. The doming that is present in the September DSMs from both systems is likely due to the results of a GCP correction issue or poor camera calibration. To improve the quality of pole photogrammetry outputs, the first step would be to improve the geolocation accuracy. The onboard GPS is very poor, especially in the vertical component, and it can be greatly improved by pairing the camera with a small RTK GPS receiver like the NLID M2 unit you can see pictured here. But unfortunately, these large, flat, and featureless surfaces, such as a beach, may just simply be a poor application scenario for pole photogrammetry, as it appears to benefit from the larger features and relief. However, the drone system does not seem to suffer in the same way, so perhaps better geolocation or maybe some other things such as varying the survey path might help as well. Finally, navigating in a straight line with no visual landmarks on the beach is very difficult, and it causes the side overlap to waver and be inconsistent, which contributes to seams apparent in the orthophotos. By mounting the pole system on an autonomous ground rover, surveys could be completed faster, autonomously, and in perfectly parallel transects. With few obstacles or steep slopes, the beach would be a very good environment to implement such a device. While the UAV is initially more expensive, its speed and ease of use make it much more practical to use. The greatest cost of the pole photogrammetry system is not the equipment, but the time it takes to implement and then process surveys. Here, the UAV is much more feasible, especially if a large area needs to be surveyed, or if the surveys need to be repeated. The advantage of the UAV system continues to increase, while the weather and flight regulations, especially the restrictions on flying over crowds, remain the only major drawbacks to the UAV approach. And in conclusion, the UAV proves itself to be an effective surveying platform, corroborating the findings of Mancini et al., Turner et al., Scarelli et al., and many others. However, the pole photogrammetry system needs significant improvement to be usable and would be best suited to smaller study areas due to the slow speed of image acquisition. The speed, ease of use, and high performance of the UAV system make it the far superior choice for routine beach erosion monitoring. So here are some of my references. And then I'd like to thank some people. First off, Manny Gonzales for helping with fieldwork. Could not have done any of these surveys without an extra set of hands. then the rest of my family for all their love and support, and also using the boat to actually get ourselves to the island. Of course, my fellow grad students for making the past couple years so great at Virginia Tech, and then the department administration, Karen Bland, Dr. Crawford, and Dr. Duran for helping me figure out everything, including how to actually graduate. And finally, the USC Coastal Processes and Sediment Dynamics Lab for getting me started in research, playing with drones and radars and other instruments. Thank you very much for coming. I'm happy to answer any questions you might have.
All right, thank you so much, Jack. Let's at this point kind of turn things over to the public. If there are questions out there, feel free to ask them. I think it's a small enough crowd that we can probably just use your mics. But if you're more comfortable just putting something in the chat, that's fine too.
Jack, I just have a kind of a practical question, if that's all right.
Yep.
Personally, in all my drone collection, I haven't done much ground control, and I wondered if you could talk a little bit more about some of the pitfalls or challenges you ran into when setting up ground control points and frustrations, etc.
The hardest part for us is definitely the PPK processing. So we gathered points and then used the logs from the MLID units to do the post processing using the core station. And there's a lot of options to do, and it's all these kind of like geodetic things dealing with different geoids, ellipsoids, datums, and stuff. There's a lot to mess up there, and a lot that's not really clear of like what you should ideally use. And I think that's most likely what caused like our doming errors, because they're so similar between both surveys. Whereas doming, you usually see it as a result of the camera calibration. I think that was most likely due to some ground control point error. We were consistent with how we corrected everything throughout all 3 months, but I think something strange happened there. So the post-processing has been the most confusing. For us, using the survey pole leaves a little mark in the sand that is really easy to pick out. It works as a really fantastic ground control point visually when you're marking it in the images, but yeah, the post-processing is definitely the hardest part, and still, I'd like to talk to somebody who really knows what they're doing about that, but yeah.
Well, that's neat, especially with what you notice in the imagery, like that little point that the pole makes. Like,
yeah.
Thank you, Jack.
Mm-hmm.
Jack, it looks like you've got a question in the chat. Are there any current commercial applications for this study, or is there a preferred method being used now?
That's a good question. I believe people are using drones commercially. Various coastal engineering firms are constantly doing this. I saw something in our local newspaper. People were using a mobile laser scanning device on ATV or something, driving it around the beach, which is another thing we had thought about doing. It would be a little bit of a big project to incorporate mobile laser scanner as well, which is like a ground-based Lidar unit, essentially. So that commercial coastal engineering firms also definitely use Lidar data. It's freely available. It's a little bit of luck of the draw of like what the government has flown lately and what's uploaded and what you can get. But people like in that Turner et al. Paper, they are actively using this as part of their beach monitoring system. So the pole photogrammetry system is much, it's not as widely explored. There are some sort of indoor mapping things that combine a ground-based photogrammetry system like that with laser scanning for indoor mapping and things. The Leica Pegasus backpack system, if you look that up, it's like $150,000, but it's really effective and makes cool maps. But yeah.
right, I think we'll wrap things up there if there aren't any more questions. But I want to thank Jack again one more time, and I thank everyone for attending and supporting Jack in the presentation. Thanks everyone.
Thank you.
Good job, Jack.
Congrats.
Thank you.